So in the last video, I showed you some examples of sequences, and for a couple of them, I kind of offhandedly pointed out that they converge to a certain number, right? Like for example, 1 over n squared converges to 0, or whatever, the other one that converged to e, right? In the case of a sequence like 1 over n squared, it's kind of, it feels kind of obvious that it converges to 0, even if you don't really know what the word converge means. So I want to kind of take a couple minutes here to kind of delve into what we intuitively understand about convergence, because the thing about convergence is that it's actually more complicated than you might realize. The definition of convergence is a bit complicated and challenging. So I want to build up to that by kind of exercising our intuition as much as we can first. So I want to basically, right, informally, convergence, right, let's see, convergence is supposed to be something along the lines of getting close to a number, which we call the limit, right? Or tending towards a limit. Now, these phrases are not nearly precise enough for us to do anything with them, and I'm going to kind of illustrate why for you a little bit. Okay, so here's an example of a sort of obviously convergent sequence, right? Well, actually, the most obviously convergent sequence would just be like a constant sequence, right? A sequence that's constant clearly just converges to whatever value it's constant at. But let's look at something more like that really exhibits the property of convergence in some substantial sense. So, the sequence Sn equals 1 over n is a real classic example, right? And that one, much like 1 over n squared, right, it just kind of decreases and tends towards 0. So this is common notation for saying that a sequence tends towards a limit, is to use this arrow. We'll actually keep using that. But yeah, so this sequence tends towards 0, and that will become true once we actually define what it means to converge. But let's think about what's happening here, right? So it is true that the values of this sequence keep getting closer to 0, right? That's true. So Sn keeps getting closer to 0. That's true. That's not enough. That's not the only reason why it converges to 0, right? Because on the other hand, but Sn also keeps getting closer to -1, right? So why does Sn not converge to -1, right? Why doesn't Sn tend to -1? Well, the intuitive reason is that it just never gets close enough, right? Never gets close enough, right? And so you have to ask yourself, what does close enough really mean, right? Because basically, you kind of have to ask yourself, what does it mean to be close, right? I mean, what makes it, what would constitute two numbers being close to each other? There isn't really such a concept of two numbers just being close to each other or being far away from each other. 0 and -1 are arguably extremely far away from each other, relative to, if you're looking at a scale of like a millionth or whatever, right? They're a million millionths apart, so they're pretty far away from each other, right? But similarly, like Sn keeps getting closer to -1 over a million, but it still doesn't actually converge to -1 over a million, right? Because it stops at 0. So it never gets closer, right, in this case, it never gets closer than distance one away, distance one away. And the same thing would be true for like -1/1,000,000. Sn would never get closer than a distance of 1/1,000,000 away from that, proposed limiting value. 0 is the only number which Sn keeps getting closer to, and it gets as close as you want it to get, basically, right? Like it gets closer than a millionth away, it gets closer than a trillionth away. Sn gets as close as you could possibly imagine to 0 as you keep going on, right? So that's kind of one of the fundamental properties of convergence, is that the sequence has to get like arbitrarily close. So I'm going to say the sequence must get arbitrarily close to its limit. Okay, now there's another issue, and I'm going to have to kind of clear this in a sec, but so this keeps getting closer concept, right? That's also something to be wary of, okay? And I'll show you why. But basically, in this case, right, it's sort of simple because 1/n, every step of the way, 1/n gets closer and closer and closer. It never backtracks, right? It never gets farther away from 0. It just gets closer every single time. And that is not actually something that we want to take for granted or that we want to require of all convergent sequences. So let me erase a little bit of stuff, right? So I'm going to erase this actually. So imagine, what if I just took the sequence Sn? So what if I replaced S7 with 3000, right? Well, actually, let's hold on. Maybe not 7. Let's say S4. Not that it matters, but just for the sake of, drawing. So instead of a dot down here, there would be a dot way, up at 3000 randomly, just out of nowhere, right? It's doing its thing, and then suddenly out of nowhere, it just skyrockets, and then it comes back down, right? Should this affect the convergence, right? The answer is no. I mean, maybe that's not clear, but I'm just telling you that we don't want this to be a problem when it comes to telling whether this sequence converges. This new sequence, right? The new sequence still converges to 0. Okay, so we have to make our definition in a way that basically ignores stuff that happens, early on in the sequence. Of course, again, early on is not a well-defined concept. Like at n equals 1,000, who can tell, like who's to say whether that's still early on or not? So really the idea is that it's like we want to make our definition in a way that basically looks at what happens when you go arbitrarily far out in the sequence. So so we are focused on the behavior for arbitrarily large n. Okay? The last thing I'll say is that actually even we can actually even adjust the values of the sequence infinitely many times, like for infinitely many values going arbitrarily far out and still preserve the convergence. So, um, so, you know, so in fact, let me just, so in fact, we could make a new sequence. Let's call it Sn prime, which equals, you know, 1 over n if n is odd, and 2 over n if n is even, right? And if you were to plot that, what you'd get would be something like, you know, this, and then this, and then this. Okay. Okay, so what it would be doing would be sort of, it would be oscillating a little bit, right? So sometimes it would go up and sometimes it would go down. Sometimes it would just alternate between going up and down. But both of these still end up tending towards zero. So this new sequence, Sn prime, still converges to zero. So the idea of, you know, consistently making progress towards the limit, again, is just, it's not really the right concept to use, because we want to consider certain sequences which maybe sometimes, that maybe they just keep backtracking every once in a while. Even no matter how far out you go, they just keep backtracking a little bit, but they still end up getting squished and getting arbitrarily close to their limiting value, right? So we still want to consider those sequences to converge. So I want to give you guys some appreciation for the diversity of behavior that functions can or that sequences can have, and how this forces us to make a definition which is sort of inherently difficult. But also on the other hand, at the same time, it should give you some appreciation for the fact that we even can make a definition like what we will make. The definition we end up with, it's like, from in a certain light, from a certain angle, it almost seems miraculous that the definition could be as simple as it is. It's difficult, but it's not terrible. So we'll see that in the next video.